Good afternoon. My name is Jean-Louis Briaud. I'm a distinguished professor at Texas A&M University and the Buchanan Chairholder in the department of the Zachry Department of Civil and Environmental Engineering. Welcome to the 33rd Buchanan Lecture. The first person I want to recognize is Spencer J. Buchanan in the first frame here next to Terzaghi, because without him, we wouldn't be here. Professor Buchanan got his degrees from Texas A&M University and MIT in 1926. He founded the Soil Division of the U.S. Army Waterways Experiment Station, now URDEC, in Vicksburg in 1932. During World War II, he served the U.S. Army Corps of Engineers as an airfield engineer. He then started the soil mechanics program at Texas A&M University in 1946. He also developed the geotechnical company, Buchanan Soil Mechanics. He had two sons, Spencer Jr. and Philip. And we're delighted to have one of his grandsons, Mark Buchanan, who is here with us. I also want to recognize the geotechnical faculty at Texas A&M University, Anand Pupala, Marcelo Sanchez, Chuck Albany, Zenon Medina, and our new addition, Navid Jafari. We're also very fortunate to have two geotechnical NA members joining our group as Hagler Fellows from time to time, Greg Becker and Youssef Hashash. We have a number of members of the Texas A&M Consortium for Education and Research in Geoengineering Practice, SERGEP, who've supported our program since 2017. Raise your hand if your company is a member of SERGEP. We have a few of them here, yes. I cannot forget all our students. So if you're a student at A&M, UT, U of H, Texas State, or any other university, raise your hand. Nice group of students. Now the program. Oops. The Buchanan booklet is on the Buchanan Lecture website. You can access it right now. We're also video recording this event, and we'll post the video on the Buchanan website within the next few weeks. We will also give the video to the Geo-Institute of ASCE, as we've done in the past for the other 32 Buchanan lectures, all the way back to Ralph Peck in 1993. Our first speaker today will be Dr. Marybeth Husty, our new department head as of 2 days ago, the announcement, who will say a few words about our department. The second speaker will be Dr. Andrew Whittle from MIT. He will deliver his 2024 Terzaghi lecture on soil models. We will take a 5-minute break, and then our third speaker will be the Honorable Andrew Card. He will deliver the 2025 Buchanan Lecture, From Civil Engineering to Politics. The event will conclude after his lecture, but we will take a group photo on the stage like we do every year before anyone leaves. Then there is a reception at Janet and I's house where everyone is invited. Now I would like to ask Professor Husty to come and say a few words about our department and looking at our future.
Thank you very much, and thank you for the opportunity to be here with you today. I'm very pleased to welcome all of you on behalf of the Zachry Department of Civil and Environmental Engineering. First of all, I'd really like to thank Dr. Briaud for his dedication and continued efforts to organize and support the annual Buchanan Lecture, and understand this is number 33, so that's quite an achievement. This event has become a treasured tradition within our department, and we're really happy to have everyone come and join us from the different schools here in Texas. As you know, we have a large department with nearly 80 faculty members and over 1,300 students. And while we are large in numbers, we are also committed to quality. The Buchanan Lecture exemplifies the importance of activities that celebrate scholarship, service, and engagement as part of a larger community. This is an important time for civil and environmental engineering and also for our department. Our path forward includes continuing to focus on impactful opportunities for our students and to support our faculty, students, and staff in their educational, research, service, and professional endeavors. The future is exciting as we consider new opportunities and challenges in a world that is rapidly transforming. I'm looking forward to working with our faculty to learn more about what they would like to do in the coming years and find some new directions and ways to continue our contributions while we maintain our focus on the fundamentals. Finally, I want to thank our distinguished speakers, Andrew Card and Andrew Whittle, for joining us today. It's an honor to have them with us. Please enjoy this special event and the opportunity to learn something new today. Now I will turn it back to Dr. Briaud. Thank you.
Thank you, Mary Beth. We look forward to working with you. Now it's my pleasure to introduce Professor Andrew Whittle. Andrew received his bachelor's degree from Imperial College in London in 1981 and his Doctor of Science degree from MIT in 1987. Andrew actually gave the Buchanan Lecture in 2013. Dr. Whittle is the Edmund Turner Professor of Civil Engineering at the Massachusetts Institute of Technology. His work deals with the formulation of constitutive models for representing the complex mechanical behavior of soils. The impact he has had on our profession has been remarkable and very broad. Indeed, the numerical tools he's developed have helped us solve some very difficult problems like the design of foundation systems for deep water oil production facilities, major urban excavations, and tunneling projects. He is a licensed professional engineer and has served as a consultant on many very large projects worldwide. He was elected to the National Academy of Engineering in 2010. The title of his lecture is Soil Models for Geotechnical Design, Prediction, and Problem Solving. And at this point in time, I would say, please welcome Dr. Whittle.
It's a great pleasure to be back here in College Station, and I'd like to begin by thanking my generous host, Jean-Louis Briaud, for the invitation to present to you today. I remember fondly coming 12 years ago to present the Buchanan Lecture, and I'm happy to see the tradition continues with the lectures today. I'm here to give a presentation or a reprise of the Terzaghi lecture I presented in 2024. This deals with the topic of soil models for geotechnical design, prediction, and problem solving. This is a topic which elicits all kinds of reactions amongst geotechnical engineers. I really want to start out with just a general observation that soil models are ubiquitous in geotechnical analyses. Whether you're aware of it or not, every time you make assumptions of elasticity or shear strength parameters, you're making a judgment on soil models. But they become essential components the moment you use numerical analyses such as finite elements or finite differences. My goal in the lecture is to share my experience in the development and application of soil models. Here I mean this to refer specifically to effective stress, strain, strength properties. I want to show you something about predictions of performance, some insights on geotechnical problem solving that I've gained, and I'm going to say very little bit about roles in design in this presentation today. I'm reminded in advance that Carl Terzaghi himself wrote a book on theoretical soil mechanics in 1943, and he emphasized that theoretical soil mechanics was never an end in itself. And I just want to assure you that's the same philosophy I'm adopting here. So it's not so much about the model, it's about what you learn from the model and the lens it provides for problem solving. Before I begin, I'm going to say the lecture's not going to do two things. It's not going to use any equations, because I think that's a little too much in a 1 hour session. And I'm not going to try and review the huge topic on the subject, because I know there are many other worthy pieces of work, but there just isn't time. So my outline, what I intend to do is I tend to start by talking about soil behavior and generalized soil models. What do they do and what kinds of observations do they encompass? In the process of this, I'll show you some very interesting work we've done recently on modeling rate effects. And this addresses or accommodates a long-standing issue in geotechnical engineering about the hypothesis A versus B relation of consolidation and creep, which was in fact first reported by Donald Taylor at MIT in 1942. I'm going to spend quite a lot of time on a couple of applications for clays, principally on deep excavations, stage construction and foundations. I'm going to talk about some applications for sands, and then I'm going to finish with a very brief discussion about more complex modeling of material behavior through multi-scale models. Some of the items on this list are already grayed out because there just isn't time in a 1 hour period. The good news today is the paper on this work is now published by ASCE, and you can obtain it online anytime. So that's the detail at the bottom. So let's start with soil behavior. I thought what I'd do is start by looking at one-dimensional consolidation and tell you a story about 3 soil models. The first figure on the left here is showing us something about clays. If you can create a clay by sedimentation process, you create a normal consolidation line shown in green, and people are very familiar with this plot in E log P space, where E is the void ratio and P is the mean stress. We assume we understand the compression behavior of the normally consolidated clay. When you unload and reload, you over-consolidate the clay, and you get a very different response indicating elastic or quasi-elastic behavior. This framework is then accompanied by the fact that when you shear clay, when you shear to large strains, you get a critical state condition. So there are 2 different states. There's a consolidation state and a critical state. This framework shows the critical state line parallel to the normal consolidation line. Everybody who's been taught soil behavior, probably in the last 50 years, has seen something like this. And you may ask yourself, what does the soil model that I'm going to describe do with this? First of all, I'm using an elastoplastic framework in the same way that the original critical state soil models did. But what I'm assuming is that we get anisotropy associated with normal consolidation. We see elasticity immediately upon load reversal. We see nonlinearity as we continue unloadings. And when we reload, we're influenced by the proximity to the normal consolidation line through bounding surface plasticity. So this is a model we called MIT-E3, which has existed since 1987. It's had a really good workout in the years since. How does this differ from sands or silts? If you deposit a sand in a one-dimensional column, you will discover that the sand gravitates and settles at some range of void ratios, Emax and Emin. And you'll observe the solid green lines. You'll see a nonlinear response. Cunningly, I've replotted the space and plotting log void ratio against log stress. But you see the curves coalesce at large pressures, many atmospheres of pressure. And we refer to this condition as a unique set of states which are controlled by particle breakage. And we refer to it as a limiting compression curve. And you can see the slope of it. All of the data you see, all of the simulation in green here, represents an elastoplastic transition, involves plastic irrecoverable deformations. And at low stresses, that's due to sliding and rolling. This framework lets us unify clay and sand, especially when we overlay the critical states of sand. And you'll notice that the critical state of sand looks very different to that of clay. It's parallel to the LCC line at high pressures, but at low pressures, it has a very small gradient in this space, and we can reach conditions where there's apparently no strength of loose sands. This is formulated in a model called MIT-S1. I do apologize for these names, which came out in the early 90s. It uses the LCC as a reference state, and the important thing to emphasize is it differs to all other soil models in that other soil models tend to measure the critical state and then relate the state to the critical state through a parameter psi referred to as a state parameter. Both of these 2 models are elastoplastic. They don't consider time, but time scaling is a huge challenge for us in clays. On the right, you can see the strain or log void ratio against log time plot that you would observe in a typical 1D laboratory consolidation test on a sample of height h1. The little black square represents the end of primary consolidation, as you can see it, and then beyond that you have creep, governed in this case by a parameter called rho alpha, as shown here. If you then transfer to the field scale, or to a much larger length scale, H2, what happens is that the time of consolidation is greatly expanded. The scale of the end of primary is a function of the drainage path length squared. You can see the black squares on the line H2. In fact, there's big confusion about what to do with H2. If you assume that the strain at the end of primary is the same as it is in the small sample, you get the standard hypothesis A. On the other hand, creep will have taken place over a much longer time period, and you get a different curve. This behavior has confounded the geotechnical profession for years because we measure both things. We describe this using elastoviscoplasticity. What's unique about this model, this MIT SR model, is we describe the viscoplastic strain rates in terms of an internal strain history parameter which relates to the history of straining. And we use a steady state parameter to be able to steer us between conditions where end of primary strain is constant and end of primary strain varies. If you put beta equals to 0, you get a unique end of primary consolidation. Of course, one-dimensional consolidation is only part of a generalized soil model. You have to represent shear behavior. To do this, in elastoplasticity, you have to introduce yield surfaces. Here is an example of a measured yield surface for a clay. The data you're seeing in the figure, the circle point at the center here is the in situ stress state. This is a block sample obtained downhole, and you can see from the arrows the different tests done in different directions in the effective stress space. The interpreted yield point is plotted in the symbols, the square symbols, and you can see an assumption of a yield surface. You'll notice that it's oriented away from the hydrostatic axis towards K0. In the modeling I'm describing, we're following that logic. We believe that the yield surfaces are anisotropic. You can see that when we first started, we used an elliptical surface, that's the green surface, and then later, with the S1 model, we used a lemniscate surface, which fits the data rather better. What is truly remarkable about soils is I can show you very similar results for a sand. The figure on the right, which has a different stress scale, the sample is initially made at condition state A and is unloaded to point B, so it has a similar proximity to the yield as the clay. You can then see the stress paths and the yield points, and you'll notice that we end up with a yield surface of similar shape, very well described by the MIT S1 yield surface. So sands and clays can be unified with a single yield surface. If you ask what causes these yield surfaces to rotate away from the hydrostatic axis, you'll end up in a more complicated story of the particle fabric, which we come back to later. For sands, we can use CT scans and we can observe contact fabric directly. And through particle contacts, we can understand why anisotropy arises. For clays, it's much more difficult. The particles are incredibly small, and we actually don't know a lot about the microstructure of clays during testing. What we do know is it's much easier to observe particle orientation in scanning electron micrographs, like the one shown on the left by Guglielmi. So what I'm asserting in this figure is the measured data, we can use an elastoplastic model with a single yield function. Inherent anisotropy in both of these cases is linked to the prior consolidation history, and rotation is related to the particle fabric. Moving forward, the first thing you do when you have a model formulated is to try and validate it. One of the special features of the models I'm describing here is we've validated them extremely carefully with respect to lab tests. What you're seeing in the figure are simulations of plane strain or undrained plane strain shear tests on the local clay from Boston, the Boston blue clay, which has been resedimented. And the data are from various sources, as you can see. The figure on the left shows traxial compression and extension, the one on the right, the simple shear mode. You will see immediately the solid lines color-coded for the model, and you'll realize that the soil model MIT E3 matches rather closely the stress-strain behavior in all three tests. To give you a sense of how this has improved things compared to prior conditions, the dotted lines are the modified CAM clay model that pre-existed my work. And you can see this is a model which is isotropic. It assumes that the critical state is unique and occurs at large strains. And you can see the stiffness doesn't match the measured data. While I think it's rather obvious that the MIT E3 model is capturing the strength, the stress strain property, and capturing the anisotropic behavior and properties of the normally consolidated clay. Of course, this is the result of a very careful prior calibration. We've gone on and taken this further. We have looked at the effect of principal stress rotation by shearing in different directions. This is a figure showing shearing in different directions relative to the vertical or the direction of consolidation. And you can see the predictions in the solid lines and the measurements in the symbols. What I want to point out to you is predictions were made in 1987. The data were actually obtained in 1990. So we're actually achieving a true prediction of anisotropy with this model. Here we stand today in 2025, 100 years after Terzaghi first lectured at MIT. And of course, you can ask, what have we learned in the last 30 years about the model? Here's the undrained strength ratio that Chuck Labb would normally plot against the overconsolidation ratio. The predictions from the calibrated model that I show on the left are shown for triaxial compression, simple shear, and triaxial extension in color coding. I put on all of the data we've obtained in the period up until 2016 on this figure, and it includes resedimented clays, intact clays by various methods of consolidation. You will see that we have a very rich data set for the Boston blue clay from the local area. If you compare it with the model as calibrated in 1987, you will see that the model is doing a very good job to bound the anisotropy at low overconsolidation ratio, but it tends to exaggerate the anisotropy at higher overconsolidation ratio. The way I expressed this at the time was to say that the model accuracy reduces for OCR 3 to 4. My approach to this is basically to accept the limitations of the model. I haven't attempted to edit the model, the formulation, and I've made no adjustment to the input parameters. So this, of course, gives us a very stable platform on which to make simulations in Boston blue clay. What we have found, though, over the years is how very difficult it is to understand compression properties or consolidation properties of natural clays. This is one of my favorite data sets. It's in Boston blue clay at a test site that MIT researchers have used since the 1960s in Saugus, Mass. What you can see on the left is the stress history data that we have at this site and a sort of column with sublayers of the Boston blue clay A to F. And then you can see one-dimensional consolidation tests for samples of the Boston blue clay, labeled B to E. You need to look very closely at this plot. You'll discover that the soil from the highest part of the clay, layer B, has a much lower void ratio than for layer E. This is a complete inversion of logic because it says the shallower clay has a much denser state than the deep clay. So this is confounding in all dimensions. You'll see that we don't get a pretty plot with just a simple normal consolidation line. In fact, that slope C sub C varies widely. In layer E, we get a sensitive clay which breaks down, and C sub C varies enormously. And you can see how this varies through the different layers. For reference, I show you resedimented clay in blue, and you can see it's kind of an average of the above. But the little table, the legend, shows you that C sub C varies from all these samples. Why does this happen? Well, it reflects complex Holocene geology of the Boston area, the way Boston is located at the southern perimeter of the last great glacial ice sheet. It's a complex history. But one of the things I would like to tell you is if I showed you samples of clay from E to B, you would see very few differences in sublayer properties. So in fact, we're confronted with the fact that clays are quite complex. And if one wants to model a clay layer like this, all of B to E are simply called Boston blue clay, you're going to have to adjust the compression parameter C sub C to reflect the stress range of interest and the sublayers of interest. Final thing I'd like to talk about on soil behavior before moving into applications is long-term consolidation and creep. I showed when we look at time effects, if we compare samples of different thicknesses, we get quite confounding results. And I'm going to compare in this slide results for a sample which is 2 centimeters thick, a fairly standard dimension, with something which is 10 centimeters thick, and you can see the actual configuration at the top. Here's some data for Pisa clay, located somewhere near the tower, and it shows the strain versus time, or log time. The time is scaled by the thickness of the sample squared. You will see in red and blue the results for 10 centimeter and 2 centimeter thick samples. If you look at the solid lines, you're looking at the strain. The dotted lines are the pore pressures. You can see as the pore pressures vanish, we reach the end of primary consolidation marked with the green triangles. You will see when I plot things this way that the red and blue curves are almost identical, meaning there is no size effect affecting the amount of creep, and therefore the hypothesis A theory looks correct. Here is an identical set of tests for Osaka Bay clay in Japan, and it's color-coded exactly the same way, but you can see there are a lot higher strains for the 10 centimeter thick sample at the end of primary consolidation than for the 2 centimeter thick sample. In other words, it obeys hypothesis B. So here we have two very well documented clays performed under identical conditions giving different behaviors. It's confounded us. We wonder whether it's due to some feature of microstructure like microfossils. There are a few of those in the Pisa clay, whereas the Osaka Bay contains a profusion of diatoms. But the truth is, whatever is causing it, we have materials which behave differently when we scale the lengths. So we built a model to try and capture this. And this model, as you can see, can produce either result. What you're seeing on the left are simulations from our model, and we're simulating one-dimensional compression of 2 and 20 centimeter thick samples. The key thing to look at is the void ratio or strain, and you can see I've put little square markers indicating end of primary. And you'll see that in one case, hypothesis A, we get a unique end of primary void ratio. That's achieved by putting beta equals to 0. And if we vary beta, you can see we achieve hypothesis B. In other words, we can calibrate this model for either of the two scenarios that I just showed you. Here is a data set from the Osaka Bay clay with samples from 2 to 5 to 10 to 20 centimeters color-coded. And again, I mark the end of primary strain. You'll notice the data are conflicting. It's hard to know which calibration makes more sense. So I offer you two calibrations. One calibration assumes we have unique end of primary, that's the top figure, and one assumes the end of primary varies. You can see we can't fit all of the data. So we can bound the data, and the data are quite confounding to us. But we have two calibrations which bracket what's going on, consistently described by this soil model, unlike any other soil models, I should say. Is this useful? Well, here's an example. This is Kansai Airport, an offshore airport in Osaka Bay. The second phase of Kansai Airport is the one we're going to look at. The little schematic in the bottom left, the pretty colored pictures are all the clay layers that we've just been discussing. We're looking at the MA11 layer, which is about 20 meters thick. It was constructed, the fill was constructed between 1999 and 2007, and we know the stress change occurring in the layer MA11. Here are the data, and you can see it's showing strain against time in years, and then the simulations with two different calibrations are shown in the solid and dotted lines, and the end of primary occurring somewhere towards 2060. You can see that they do indeed bracket the data that are available currently, but it's going to be very interesting to find out what happens over the next 20 years or so. But we claim we've now got a model that can handle these diverse observations, which we think is important. So we can bound the predictions of long-term settlement. Okay, let me turn now to using these models in real situations, real-world applications. I'm going to start out with a work we did on excavations. We've done a lot of work on excavations over the years. I wanted to show you some results for a single project. It's called the Courthouse Station. In the top left, you'll see the site plan. Boston Harbor is at the top. This is an area of South Boston, now called the Seaport District. The project site is over here, and the red is the Central Artery Big Dig project that was built a little before the time of this project. The site, if you look at the vertical cross-section, you can see is a supportive excavation, a temporary supportive excavation with 5 levels of bracing and diaphragm walls that tow out inside the Boston blue clay layer. You can see we're far above a bearing layer. The cost of extending the walls down into the bearing layer is expensive. The alternative to strengthen this support system would be to use ground improvement below the grade. The total excavation depth is about 17 meters. We asserted at the time this project was proposed that it could be built safely without any ground improvement as a floating support system. Our predictions using the MIT model were included in the construction bid package. And we followed up with Class C predictions after the construction was completed. The only thing that changes between Class A and Class C, as far as you need to realize, is we updated the excavation timeline to reflect the actual construction, and we used the actual measured strut preloads. This project was very challenging back when it was first proposed because there was a very low margin of safety against basal instability, and therefore a great deal of nervousness about how to do the construction safely. The photograph shows during construction. You can see that the site is not bounded by many major structures. In fact, at the time, the area was just parking lots. If you visit today, it's a new downtown, a glitzy new seaport district. But back at the time, it was an area of fairly derelict land. The student who did the Class A predictions worked for the company that installed the monitoring data, and she actually designed the instrumentation and monitored the project. I was not involved at that stage. I only got involved in Class C after the project was completed and closed out. Why is this such a great project? Well, we had a lot of soil property data available in South Boston, thanks to my colleague Chuck Ladd. He did a very detailed site investigation in the vicinity of the project I'm talking about. You can see the stress history, the familiar plot from people working in Boston of a clay which is very nearly normally consolidated at depth and has a deep over-consolidated crust. You'll see in the middle panel undrained strengths comparing measured data with model representation, and on the right, hydraulic conductivity. So we had a lot of useful data for calibrating site conditions. How did we do? These figures show at a central section of that excavation predictions of the wall deflections in the bottom two panels and predictions of surface settlement troughs in the top two. The Class A are in the dotted red, and the purple or blue are predictions made Class C. Hopefully you can see, looking compared to the measured data, which are the symbols, you can see that the Class A predictions overestimated wall movements. That is very exquisitely controlled by the fact we didn't know the strut preloads at the time of the design bid going out. When those preloads are included in Class C, you can see that the wall deflection is almost perfectly matched. So this is a remarkable result because we haven't fitted any data. We've used soil parameters obtained before anything was built. The surface settlement trough is also quite well developed for both of these cases. So we thought this was a very consistent result. We also looked very closely at measured strut loads, which were well described, and we looked at pore pressures beneath the base of the excavation, where we discovered, of course, in Class A, we overestimated the construction or excavation time period. But if you look at the totality of these results, they're a remarkable judgment on our prediction, because we made predictions in advance, no adjustment of soil properties or soil modeling. So it's possible to make very accurate predictions. And this is one of the very few cases where I can say we were involved from the start. During the course of this work, the soil modeling told me one thing, which is it was extremely important to have accurate stability analyses. And we really felt that the stability analysis may be misleading. So I got involved in improving stability analysis in geotechnical engineering using a technique known as numerical or finite element limit analysis. I've just abbreviated it NLA. This was done in collaboration with the late Scott Sloan from the University of Newcastle in Australia. What you do here is you use a conventional finite element spatial discretization, but you solve upper and lower bound plasticity for rigid plastic material behavior. If you consider what I just showed you for an excavation, this is a sort of simplified version of the problem. You can see we have a set of struts which are designed not to fail. We have a wall which bends, that's the plastic moment parameter, and we have a clay, and I've chosen here in this example to show you a uniform clay with undrained strength SU. The embedment depth D of the wall contributes to the stability of the excavation. Here are the results we obtained as a measure. The factor of safety is surrogated here with the stability number, gamma H over SU. This plot I actually showed in the Buchanan Lecture in 2013, and it's showing a combined failure of the wall and the soil. And you can see this on the horizontal axis. The relative strength parameter is the ratio of the bending resistance of the wall to the undrained strength and the embedment depth squared. If you go to the left-hand side of this plot, the wall bends and fails very easily. You go to the right-hand side, the wall is strong enough that it doesn't fail, so only soil fails. When I came in 2013, I proudly showed off what's written here as the original NLA, the colored bands. And I said, this isn't a bad estimator of the factor of safety. You can see that we can bound the stability for different geometry conditions of excavation support systems. I was quite criticized for this because people said it's not accurate enough. Nowadays, we have commercial finite element codes that solve these problems. We have a program called OptimG2, which has some very clever adaptive meshing. So I asked one of my current PhD students to rerun the analyses. And in an afternoon, she came up with the tram lines, the dark green and the triangle lines in both the two bands. She came up with these results in a short afternoon of work. And you can see we now have almost perfectly accurate results, and you can see we're narrowing down that factor of safety, so we have a really good predictor. I would assert today for many geotechnical problems we can make very accurate predictions of stability. So this is a remarkable accomplishment, and it's the first time that I'm aware that we have essentially a design method dealing with combined failure of the soil mass and bending failure of the wall. Terzaghi, of course, used limit equilibrium back in the 1950s and 40s. He didn't consider the failure of the wall, and his analyses are on the unsafe side, and that's what I'm showing with the dark triangles, the black triangles. So we reran the courthouse station. We asked if we had the best tools that we have today, if we had had them back at the time, what would our assessment of factor of safety be? And we came to a number something in the order of 1.35 to 1.37. So the margin of safety against stability when we had better analysis was somewhat higher than when we first did the Class A predictions, which I suppose is a relief, and maybe one of the reasons the project worked out so well. Of course, when you do excavations, you're primarily interested in undrained shear behavior. Consolidation occurs only if you leave the excavation hole open for extended periods of time. In contrast, when you build things on top of soft clays, you rely on the consolidation process for the soil to gain strength. This is a case study which was in sort of the archives. It's the failure of an offshore rock-filled breakwater in Sergipe, Brazil. Here's the cross-section. You can see that the underlying stratigraphy involves rather prominently a 7-meter thick layer of soft clay. The construction involved creating a geotechnical berm, which involved barge dumping of boulders directly onto the surface of the sand. And then sometime after the creation of stage 1 geotechnical berm, the rock fill was constructed by crane placement of boulders and was originally intended to reach a height plus 6 meters. Failure occurred during the construction of the stage 2 rock fill. Again, I've picked this case study because we had a lot of good data associated with a forensic study done by Chuck Ladd and Shunmin Lee in 1993. They ran a series of lab tests. They actually calibrated both CAMCLAY and MIT E3 soil models, which we've seen already. They didn't, at the time, do any analysis of stability by these methods. So how do you do undrained stability for a stage construction? Well, one approach is to follow Ladd's Terzaghi lecture from 1991 and do an undrained stability analysis. How does this work? Well, what you do is you consolidate the clay, you actually simulate the consolidation, and then you periodically interrogate the model by asking what is the available undrained resistance and what is the factor of safety based on that. So this is doing what Ladd would recommend from his 1991 Terzaghi lecture. The property that we're using is computed by the MIT E3 soil model. So what you see on the figure on the right is a measure of the factor of safety, which is the weight of the stage 2 compared to the actual weight. And you can see the construction day, I put it on a log scale. The actual failure occurred with the red diamond. And you can see the MIT model showing how the factor of safety would vary with time. And in fact, you can see that more than 1,000 days are required to achieve substantial consolidation and stabilize the structure. The model doesn't predict accurately the time to failure, but it predicts very closely. Whereas simpler soil models based on isotropy overestimate the factor of safety. These types of models give us rigid plastic failure mechanisms. They show us where the failure would take place. So you can see the failure would occur both to the landward and seaward side, which is what was observed. And they show relative displacements. They show instantaneously where everything would move at failure. And these are consistent with the data that we had. A second, more challenging analysis is to see whether the model could actually predict deformations and pore pressures that develop over time. This involves us to know the fill elevation and the actual construction sequence. And you can see it's easy enough to work out the maximum height of the fill, but actually the construction of the geotechnical berm, we don't know the sequence of filling. We just know it was crane dumped. So the analysis of stage 1 geotechnical berm is quite challenging for us. We have to make assumptions. This particular site did not have a lot of instrumentation data. It had a single inclinometer, VT1, and it had some pore pressure measurements. When we do our analysis, you can see that when we came to the simulation of deformations, we do quite well, providing we use the Model 2, where we assume that the barge dumped spreads out laterally across the structure. That works quite well for us, and we end up with quite reasonable predictions of the magnitudes of the pre-failure deformations and pore pressures. On the bottom right, we found some of the pore pressure measurements greatly exceeded the surcharge load, which is a physical impossibility. So we know the data are not very reliable. But the predictions of earlier stages were very well done. So sometimes there's a good reason for discrepancies between the model and data. I'd like to turn to the last example on foundations. This is the Millennium Tower, known as 301 Mission Street in San Francisco. This is a 60-story, 184-meter high, reinforced concrete frame building with a 1-story basement. It's been much in the news. It has a 3-meter thick foundation mat, and it's founded on piles. But you'll notice those piles toe out. They're about 16, 17 meters long. They toe out in the sand layer, the yellow layer. The whole structure is underlain by what's called the Old Bay clay, which is a very stiff but lightly over-consolidated material. The original designers thought that that material would be very stable as a foundation. They didn't just build a tower at this site, they also built a podium structure, which is a 38-meter high mid-rise. And before they could build that, they excavated a 16.7-meter deep basement with another mat. There was a perimeter soil mix wall, but one of the biggest challenges in their design is they didn't cut off the groundwater conditions inside the basement of the podium basement. So as a result, they inevitably dewatered the area around the basement of the Millennium Tower. The construction of the Millennium Tower and podium, which this is the site of those, was finished in 2009, and ground movements and tilt of the structure were already prominently known and exceeded the design expectations. The adjacent projects you can see in colors were built in the years afterwards, including the Trans-Based Transit Center, which used a large buttress to try and prevent damage to the Millennium Tower, 350 Mission Street, and the Salesforce Tower, all completed in the years after the end of the construction of the Millennium Tower. My involvement in this was part of a whole group of people going through the mediation process about coming to a financial settlement of the costs associated and the repair costs for this project. Why is this a very interesting project to use a soil model? Well, we could say immediately by just looking at the stress change that the tower was going to load the Old Bay clay into its normally consolidated region. So it was going to exceed the pre-consolidation, at least in part of the layer. And therefore, we know as geotechnical engineers, we expect larger settlements. You can see from the pre-consolidation stress versus the estimated final state of stress, this condition. It's important to understand that when you load to a condition like this, a large fraction of the movements can be attributed to creep settlements. This is well known in the profession. We also had many other data points. This is all, in fact, due to a very extensive site investigation and laboratory test program performed by ARUP, who were the geotechnical engineers of record for the Trans-Bay Transit Center. These data were obtained after the end of Millennium Tower construction, so they wouldn't have been available to the original designers. When I joined the project looking at this, we also had some special test program run by our colleagues at UC Davis, Jason DeYoung, who had measured how the compression property varied with strain rate. This is a key parameter that can be used to calibrate the MIT-SR model. So we found ourselves in possession of a soil model that we believe could represent the Old Bay clay and capture all the behavior that might be affecting the properties of the tower. I'm going to show you some results of foundation settlements. The first one is simply looking at the tower. If the only thing they built was the tower, what would we have predicted? And you can see I chose for the measurements just the midpoint. And then the simulations you see are color-coded according to the corners of the tower. So you see the smallest settlement in the southwest corner and the largest in the northeast. The solid lines and dotted line, the only difference there is the effect of a drawdown associated with podium construction and lasting until 2020. This was a 4.6 meter drawdown. You can see that the drawdown adds to the settlement, but it doesn't affect the direction of the tower tilt. The end of construction, you can see, has already achieved more than 20 centimeters of settlement. We've done models which are much more complex. Here's one which includes the podium construction at the same time. Same color coding, same everything, and you'll realize that the tower only would tilt south to north, whereas with the podium, it eventually moves towards the west. So there's a different orientation of the tilt. So there's a large effect of the podium on the mat tilt direction. It's hard to look at data for the mat measured directly because there's all kinds of details in the structure which make mat measurements kind of challenging. But you can easily look at the roof level deflections of the tower. In fact, if you assume there's a planar deformation of the foundation mat, you can map out the tilt in both the north-south and east-west direction. And that's what's shown in this figure. The data are in the symbols. And here I'm quoting work done by my colleague Yusuf Hashash, who used a best flip plane. So you can see we've got the tower tilting towards the north. You'll notice that there's a large tilt at the end of construction and a very slow increase thereafter. You will also see in this figure the model predictions of the tower and podium together. And you'll notice they predict the same amount of tilt towards the north. In other words, we're capturing this phenomena quite well. The drawdown and podium have little effect on the north-south tilt. You'll notice some features in the data that are not predicted. That's because this model doesn't include the buttress which is installed. Installation of the buttress causes the tower to tilt towards the south. That's what that bend is. And we didn't include the other features of the other constructions. Now look at the tilt towards the west. You will see the two models differ hugely. The tower alone is in blue and the tower and podium in purple. But you can see they differ in direction. The measured data suggests the tower tilted to the east initially and then slowly progressed towards the west. We're not capturing this at all. What we're in fact saying is that podium construction had a major impact on end of construction predictions, which it really isn't realistic at all. And the subsequent east-west tilt is not well predicted. Here's an example. If we move the tilt up here, you can see we're underestimating what was observed. This puzzled us for a very long time. We haven't tried to fit the data, but we were relieved when we realized that everyone else was having exactly the same experience. Other experts from other parties had exactly the same experience. So it tells us there's something more to be found out about the behavior of the tower. I'd like to turn to sands. Sands are very tricky to model also. This is a recap of what you can get with a model such as MITS-1. You'll see that the model can predict very diverse stress, strain, strength properties and behavior in drain shearing in lab tests. That's what these green and blue lines are showing. They're showing the effect of confining pressure and density on the stress strain properties. They actually show things that all soil mechanicians know. Dense sands dilate, loose sands contract, and the amount of dilation is very dependent on the stress level. This is the result of this remarkable PhD thesis of the late Juan Pestana. If you summarize peak friction from these plots, you can see that we can map it as a function of the effective stress at peak condition and the void ratio. And again, this is color-coded to the measured data from numerous sources. And you'll see there's quite a lot of scatter in the data, but I think you'll agree the model has a very credible representation of the drain, stress, strain, strength property of the soil. What you probably can't see so well from the figure on the left is that the model is predicting a unique critical state. And this is the E log P, and the red line is the critical state predicted by the model. That's for this data set. If I expand the view to a wider range of stresses and I add the data, you'll see that the model predicts the critical state line rather accurately, which is a remarkable outcome of this model. So we have a model that's capturing drain stress-strain properties and the critical state conditions, all with a single set of parameters. How is this useful to us? Well, you can consider interesting problems. Classic geotechnical problem, bearing capacity. When I teach bearing capacity to undergraduate students, I often show them the results of model tests performed by De Beer and Vesic in the 1950s. What you discover is that there are different mechanisms of bearing resistance that appear according to the density of the sand. The top figure, general shear, is only ever observed in dense sands and resembles closely the Prandtl failure mechanism. The punching shear is for loose sands and looks completely different because there's much more compression of a loose sand. Existing soil mechanics techniques of estimating bearing capacity do not capture these mechanisms, but a soil model that represents everything I just showed you can. So here is predictions of strains and deformations occurring under a footing, a large footing. The top figure is a very dense sand and the bottom one a loose sand. They're color-coded to reveal that difference that you see on the left. The orange is the zone of dilation, where the volume is increasing, and you'll see large upward movements of the surface adjacent to the structure. The orange throughout the mass is showing that we're getting volumetric increase throughout the mass. When you go to a loose sand, you'll see a large zone of blue indicating compression and almost downward movements almost everywhere and very little dilation anywhere. So this comes out of simply starting the model in a simulation at different void ratios. And therefore we can predict the stress-strain curve. So we are correctly predicting qualitatively the deformation resistance of the foundation on sand, of a surface foundation. We've done many of these studies and compared them with measured data. We've looked in particular at the bearing resistance. This is showing a summary of the bearing resistance factor, or bearing capacity factor N gamma, against the footing size. So as you move to the right, you're dealing with much larger footings. I've color-coded this to show the effect of the initial void ratio, and I'll point out the measured data in the symbols, and they match rather closely. So we know that N gamma varies hugely with the initial void ratio and with the size of the foundation. Bearing problems in sands are not always that important, practically speaking, but this provides a basis for something else completely new, which is we can now consider spatial variability in sands. Varying void ratio as a state parameter, we will capture all of the stress, strain, strength properties through changes in void ratio. And therefore, we can start to represent realistically what happens at large scale. When we produced this, people said, who cares about large foundations on sands? Here is a picture of the gravity-based foundations for offshore wind turbines to be placed offshore Normandy in France in 2021. These are large gravity structures. The base is 30-meter diameter, and they're sitting directly on sand layers. So I would assert that what I've just showed you is going to be extremely useful for this kind of problem. Last problem, sands, I'd like to sort of draw you to another problem. The last 5 or 6 years, I spent a lot of time looking at stability of tailings. And this was really motivated by a video which appeared in January 2019. What you're seeing in the video here, there's two snapshots, A and B. They're about 10 seconds apart. What you see on the left is an 87-meter high dam that was built over a period of 37 years, and it stores iron ore tailings in Brazil. The dam was constructed and finished construction 3 years before this failure occurred. What you see in B is the spontaneous liquefaction of this entire mountain of tailings. It's an extraordinary piece of video, and it comes from a security video. This is actually the Correjo de Feijão Dam number 1. It released 12 million cubic meters of iron ore tailings. More than 260 people died, and the initial compensation settlement was $7 billion. I read in the New York Times, ongoing environmental litigation in Brazil has added another $25 billion associated with this project, and the Brazilian government has mandated an end to all upstream construction in Brazil. Not only are they doing that, they are dismantling many existing upstream constructions and relocating them at enormous cost. So what is an upstream construction? you can see the cross-section of this structure. The tailings are the red, yellow, and green. This is the material which was deposited through hydraulic fill. The red are low permeability slimes, the yellow are high permeability sandy-like materials, and the green are something intermediate with more silt content. The hydraulic deposition ends up with a large spatial segregation and difference. The dam structure is permitted in a series of rises, and as I say, this took almost 37 years. So how do we analyze spontaneous liquefaction like this? This is clearly a very dangerous type of failure. Most people start out by saying, well, it involves undrained shearing of the tailings material. So let's look at the simulation of undrained shearing of sands. You can see in this figure stress strain curves and stress paths measured for a sand, Toyura sand, and then the simulations of the MIT S1 model. And you'll notice there's generally good agreement. The results show a range of void ratio, two different void ratios that show a range of consolidation stresses. It shows critical state at large strains, and the agreement with the data is very good. Some of these tests, number 2 and 3, show instability points where undrained shearing is associated with a peak resistance, and that's indicated with the red dot. If we go to even looser states, we can find that the sand in undrained shearing will exhibit a peak, a very large post-peak softening, and very low residual critical state value. This is the concern in liquefaction, that you exceed the peak and you get a massive loss of resistance. The model works well for this. None of this is enough to explain failure of Feijão. For this, we need to consider triggering. And triggering says that the dam is stable, and it's stable, and then until something happens, something triggers a failure. So this is showing the shear stress, vertical effective stress. This is like looking at states of stress in a slope with different slope angles. Drain shearing in green would enable me to show a stress path going all the way up to the Moore Coulomb failure envelope, and things would be perfectly stable. You would get a drain response which is stable. So the green is completely stable. The data in colors are what happens when you start doing undrained shearing at different conditions along that path. And hopefully you can see by looking at the red one, delta tau is the perturbation shear stress that you can impose from that starting condition, which will bring about a peak resistance. And you'll see the perturbation gets smaller and smaller the closer you move up that drain stress path. In other words, as you increase the slope angle, the perturbation you can tolerate gets smaller and smaller. And this is obviously a huge issue in the design of tailings structures and others. MIT S1, I haven't tried to emulate these particular data set because it comes from another site, but I just want to show you that qualitatively we get exactly the same result for the MIT S1 soil model. In other words, we have a model that is capable of predicting triggering. We investigated this at length, trying to figure out what we could say about triggering. You can see in this figure the stress path on the left, and essentially the green is what I just showed you on the previous figure, but in a different stress space. And then the color-coded lines are the undrained paths. If you look at the blue line, you can see that we reach a point here where if we convert to undrained conditions, we have instantaneous failure. In other words, triggering is negligible. That condition is obviously extremely critical for us. And it turns out we can predict where it occurs. It turns out there is a stability index which applies to all elastoplastic soil models. That's what's shown in this cartoon over here, is the stability index. I didn't include the math behind it. What you can understand, though, is that if I compute lambda equals to 0, that means I've got essentially I've got no undrained reserve capacity at all. And so this is a real problem. The figure on the right goes one step further. Most tailings dams fail because the water pressures in the dam keep increasing. And that's represented by the horizontal green line. And again, you can do an undrained perturbation from anywhere along that path. And you'll see I've marked with a cross the critical location. So we know where the failure can occur. And we can map out the friction angle where it occurs. And in fact, we find for this particular set of parameters a critical factor of safety in terms of tan phi CS divided by tan phi X, 1.44. In other words, if the factor of safety against drain failure is below that number, we may have no undrained capacity available. Now, the beauty about this methodology is we can do it for any soil model, and there are many different soil models being used today for liquefaction analysis. So this could be applied for lots of other pieces of work. It also highlights, unfortunately, the limitations for interpreting instability. And quantitative predictions are going to be strongly dependent on the model you use and the calibration of the model, unfortunately. Why is this a challenge? Well, properties of the tailings vary depending on the particle size distribution. So the segregation produces different critical state line locations, different particle sizes, and the result is if I wanted to simulate the tailings with an advanced soil model, I would need to have very good knowledge of stratigraphy and of in situ state. When we came to analyze that failure in Brazil, we realized we just didn't have that data. The advanced soil model would contain too many uncertainties. And so it became very apparent to us you needed a simpler approach. So we went back to numerical limit analysis, and for this we used extremely simple assumptions on the parameters of the tailings materials themselves. Our biggest uncertainty was in the stratigraphy, and we varied it, and we measured or computed upper and lower bound stability. And you can see the mechanisms of failure shown in the lower and upper bound analyses are basically the same. They match what was observed in the field, and the factor of safety is incredibly low, 1.12 to 1.19. So the mechanism is consistent with failure, and what we found essentially was that this structure was a disaster waiting to happen. The designers thought they had a much higher factor of safety than was actually operating, and in fact our analysis revealed that a minor perturbation could set this thing off. So now there's a lot of people trying to figure out what that minor perturbation might be. Finally, I want to talk about complex soils and multi-scale modeling. I think this is where the future of constitutive model lies. I was just going to show some results for a special soil called Old Alluvium, which we encountered in a tunneling project in Puerto Rico. What you see on the figure is the picture of the tunnel that we were interested in, which is a stack drift tunnel. I want to point out just the soil layers. They're referred to as lower sand, middle zone, and upper clay. These are residual soil. It's a residual soil profile. What's unusual about this is the sand is the unweathered material below the water table, 20 meters below the ground surface. The middle zone is more highly weathered, and the upper clay is very highly weathered material. So the parent material is a sand. Lots of scatter in the conventional parameters that geotechnical engineers would obtain. The intact strength of the material, both the upper clay and middle zone, we obtained from block samples, and you would say these are cohesive frictional materials. They look like cemented sands. We did far more investigations of the microstructure, and we realized these were very complicated materials. We found there was lots of clay, in particular a species of smectite called nontronite, and we discovered there was a lot of iron oxide. That's shown in red, goethite and hematite. So we did a very extensive mineralogy of this, quantitative mineralogy, and then we came up with a conceptual model of the microstructure based on all of this information. What you need to understand about this material is the particles are no longer solid silica particles, they're aggregates. They're aggregates made up of clays which are also aggregated. So there's multiple scales of porosity present. The iron oxide serves as a cement, and the iron oxide suppresses the swelling behavior of the underlying clay mineral. I can prove this to you rather exquisitely by showing you what happens to the engineering properties. The left panel shows a compression test, and as you see, as we compress to higher and higher stresses, when we unload, we get more and more swelling. In other words, the swelling property of the clay is suppressed in the in situ state. Once you get above the yield point, you start to break down the structure, you break down the aggregate, you get more swelling. CV tells us consolidation timeframes. The blue is the starting point of this test, and you can see we end up 3 orders of magnitude lower in CV. In other words, we've transformed an intact cemented sand into a high plasticity clay. The figure on the right simply compares the hydraulic conductivity with behavior of other resedimented clays. And at a given void ratio, this material is much more permeable than other clays. So this is the features I want to draw your attention to, summarized in the bottom here. We've tried modeling this. We've tried modeling it. It's difficult to model, because we try to figure out how the disaggregation process can be quantified. We ended up using cation exchange capacity as a surrogate parameter because it would represent for us how much of the clay was available to swell. And so we built a model with Maria Nicolinacu that would represent this. In the process, we had to model or simulate the microstructure of the clay, which essentially involves electrostatic repulsion between clay particles, resulting in a swelling pressure at the macro scale. The mapping between micro and macro scale, we actually took some notice of work done by Alonso in the late 90s. And this is how we made this linkage. We have a model which now describes quite well this very complex compression behavior. But what's most interesting about it is we've been able to take this and apply it across a range of depths within the clay. In other words, for the first time ever, our modeling approach is simulating properties and breakdown of different parts of a residual soil layer. So I think this is an unusual result. So it's just one example. Finally, to summarize, if you're interested for more details, by clicking on the QR code, you can see the rest of the paper. So the soil models that I've described reflect an understanding of soil behavior, and really they've benefited from advances in lab testing capabilities. I've shown that accurate predictions are achievable, both of deformations and stability, but they always require good site investigation and careful model calibration. I've also shown that we can do credible scaling from laboratory to field in this process. The constitutive model offers some insights, both in the solution of complex problems, for example, that latent instability in the hydraulic fill tailings. And I've shown that we've learned from complex models to build simpler analysis, such as numerical limit analysis, to improve stability. And then finally, at the end, I've given an illustration of multi-scale models. The paper contains other examples, which I think will be of interest to some of you. So I'd just like to end by thanking or acknowledging people. I've got to thank, first of all, my wife, who has been incredibly supportive all these years. I need to thank my former MIT colleague, Jack Germain, who really has taught me all about lab methods and soil behavior, and it's been a very productive relationship for many years that I value. I need to thank all the people who helped me compile information for the lecture, and I'd like to thank the mentors who set me on this path, my thesis advisor, Mohsen Bali, my undergraduate advisor, David Haidt, and Chuck Ladd, my faculty colleague at MIT. And then finally, I'd just like to thank all the students who made this possible. I've been blessed at MIT to work with some really, really wonderful students. I hope I haven't missed anybody off this list, but these people I've worked with very closely over the years and value very much. And finally, thank you all for your attention. And the motto to end with for me is, unleash your natural curiosity. There's always more to discover out there. Thank you very much.
Well, thank you, Andrew, for this wonderful lecture. We're now moving to the 2025 Buchanan Lecture. It is my pleasure to introduce the Honorable Andrew Card. And we also have his wife, Kathleen, with us. Very happy to have you. Thank you for coming. When our committee selected Andrew Card as our 2025 Buchanan Lecturer, I got on the phone and relayed our invitation to him. One problem I faced was, how do you call a person with such a stellar pedigree? I got a clue from Linda, his assistant at the White House, who said, you can call him the Honorable Andrew H. Card, Jr., because he was Chief of Staff for President George W. Bush from 2001 to 2006. My reaction, well, that's a little bit long. She said, well, then you can call him Secretary Card, because he was Secretary of Transportation under President George H.W. Bush from 1992 to 1993. But many of us would call him simply Andy around the White House. I happen to know Andrew Card a little bit through mutual friends from the Bush School, and two things have struck me as I briefly interacted with him. He's very smart, and he's very unassuming. And because of this remarkable combination, I have the utmost respect for him. Where could he get such a wonderful combination? Well, he's an engineer. Furthermore, he was involved with the Bush School of Government at Texas A&M University at the highest level, so we'll definitely claim him as one of us. Indeed, Secretary Card got his bachelor's degree in structural engineering from the University of South Carolina, and then attended Harvard. His biography is remarkably impressive, and I hope that you will guide us through your journey and how you went from engineering to politics, what it takes to succeed in this arena, and that you will help our many students consider a life of service in politics. Please welcome Secretary Andrew Card.
I have bounding surface plasticity. I'm excited to be with you. Yes, first of all, I understand what Boston blue clay does to structures in the Boston area. I parked the car in Harvard Yard, so I'm from Massachusetts. I met my wife in the 5th grade. She and I use a lot of language that some people in Texas don't understand. But I am honored to be here. I'm surprised to be here. Yes, I'm a proud engineer. I was not a stellar engineering student. But I loved engineering because engineers really are the most ethical of all disciplines. Engineers understand that if their results don't work, people could be hurt. And so I have found engineers to be particularly attentive to doing the right thing. And they also take great pride in testing their knowledge every time they make a decision. So you don't get stuck on stupid the way they do in political science classes. The truth makes a difference. But I'm an engineer and a politician, and yes, that is frequently described as an oxymoron. I don't know whether I'm the oxy or the moron, but there aren't many engineers in politics. And I was asked today not to present a treatise on engineering, but to invite you to recognizing that you are needed to participate in our great democracy. And that means politics. The politics is not a dirty word. It's actually a noble calling and responsibility, and it takes sometimes the title of public service. And I invite you to be a good engineer because we need more good engineers in politics. And you should understand that if you are an engineer, there are many ways that you can contribute to the state of politics, the state of our nation, and the state of civility. Because you also learn to challenge yourself and invite others to challenge you as well. And you learn in that process. So I was asked to speak not about what it means to be an engineer. You know that, or you will come to find out what it means. And I'm going to tell you how I got involved in politics and why it's worthy of your consideration. First of all, engineers are welcomed in the political environment. Not many engineers look to be welcomed, though. So very few participate. We've only had 3 presidents that were engineers. One, pretty remarkable one, Jimmy Carter went to the Naval Academy. Herbert Hoover was very well trained as an engineer, very proud engineer, did a remarkable job as president for the engineering profession. He gave us the Hoover Dam and other things. And then we had, I'm going to say, Thomas Jefferson. Thomas Jefferson didn't call himself an engineer, but he actually practiced a lot of engineering in the way that he tried to build buildings that would reflect, I'm going to say, the opportunities of a brand new country that he was very proud to help have started. So, first of all, I would like to invite you as an engineer to open your eyes and ears and mouth about what it means to be involved in politics. And I admit that I come from Boston. I grew up in a family that is from a suburb of Boston, Holbrook, Massachusetts, 15 miles south of Boston. It was a bedroom community for people who worked in Boston. It was also a kind of a tough community. I used to say, no matter which side of town you're coming into the wrong side of town. But my wife made sure that I was on the right side of whatever the right was that I didn't recognize when I came to town. And I did meet my wife in the 5th grade, and we've celebrated our 58th wedding anniversary this year. So I'm proud that she's with me, and she's had to put up with an engineer for a long time. I have to give her credit for giving me a phenomenal gift. When I was in engineering school, there was something attached to my belt all the time. It was called a slide rule. You're lucky you don't have to carry one around. I had to carry one around because I had to do a lot of calculating, and we did not have little boxes of knowledge that we could carry with us with the answers. And that required us to use a slide rule. I love to challenge engineering students today to work the slide rule with me. I don't think you can do it. I also would call attention to the gift that my wife gave me when I graduated from engineering school. And she was proud that I was graduating as an engineer, and she gave me a Bomar brain. It looked kind of like your cell phone, but it was the first handheld little computer that would actually do some work. And the Bomar brain that I had came from Massachusetts, Maynard, Massachusetts, where they were invented and made. And this little device could add, subtract, multiply, and divide. It didn't do much more than that, but that was pretty significant when it came from a generation of slide rules. My wife gave me that as a gift. I still have that Bomar brain, and I will admit the little device that I carry around with me now, called a cell phone, has got a lot more to do with success than my Bomar brain did. But why would I get involved in politics? First of all, I was privileged to grow up in a family that the word politics was not a dirty word. And I had a grandmother, my father's mother, who was very influential in my life. And she didn't live far away from me, was across the street from where I was growing up. So I didn't have to go over the river and through the woods to Grandma's house to get wisdom. And in fact, if I hadn't been doing my homework well, I was sent to my grandmother's house to do it well. And sitting at her dining room table, there was always a blessing, but I was not allowed to pick up an eating utensil without responding to her question, "Tell me something from the newspaper today." Inevitably, every conversation at the dining room table centered around either Boston sports or politics. So I came to recognize that there's a lot that I didn't know, that I pretended that I knew, that my grandmother taught me to pay attention and acknowledge. She was a great conscience for me, and she also encouraged me to get involved in politics. The remarkable reason for her to be involved in politics is that she said she was very blessed to live in this country. And she said the Constitution that we all celebrate is a remarkable document, and the first word in that Declaration of Independence is we. It's our government. And my grandmother had gone to college and graduated in 1894. That's a long time ago. before many women did have a chance to go to college. She graduated from college, then ended up being a professor. There weren't very many women professors at that time. And she told me when I would talk about politics in this little session at the dining room table that I wasn't paying attention enough to what was going on in the government. And I had to step up and take a look at it. And she said, you know, when I was your age, the word we in the Constitution didn't apply to me because I didn't have the right to vote. I didn't have the right to serve. But you are part of that we, and when I became part of that we, it changed my life. That's what my grandmother said. She said she was the first woman to register to vote in the town of Holbrook, Massachusetts. And she was very proud that I registered to vote, that I graduated from college, and one of the first things I did when I came back to Holbrook, Massachusetts was to register to vote. And I voted and decided to run for the planning board in the town, ran a campaign, knocking on doors, talking to people, and got elected to be a member of the planning board right out of college. I graduated in January, and I was serving as a member of the planning board of the town of Holbrook in March, right after the elections. By the way, Holbrook is a small town, and a lot of people were invited to participate in government, and they would answer that call because they had open town meetings that would be attended by people, and they'd talk about tax rates and curb cuts, cul-de-sacs, lots of things that engineers pay attention to as well. But my grandmother, when she told me that she was the first woman to register to vote in Holbrook, I'm not sure I really believed her. But after running for local office and serving, and then running for state representative, and running and losing in a campaign, and then coming back and winning in a campaign, and then running for governor in a forgettable campaign because I didn't win at all, but I was called a hidden winner, I decided to check my grandmother's veracity and went to the town clerk's office and went through the records with the town clerk, and yes, my grandmother was the first woman to register to vote in Holbrook, Massachusetts. And I found out that she also, when she registered to vote, took out papers to run for the school committee in the town of Holbrook. And she was the first woman to stand in line and vote. She also was the first woman to win an election in Holbrook, Massachusetts, and she served for 20 years on the school committee in the town of Holbrook. She was married to an engineer, a chemist engineer. And my grandfather, her husband, served in World War I. And he worked as a chemist, helping to come up with ways to get away from the challenges of World War I, which were primarily from chemical weapons that were being used. So she took what he was doing and talked to me about what I should be doing and looking at being an engineer or a chemist and what was I going to do when I grew up. And she motivated me to be in engineering. My grandfather did too, and he was pretty proud when I graduated, not because my grades were good. I graduated because my grades just barely passed the record of saying, you earned it. But I earned it and I was pleased. But I ended up getting involved in politics, so I don't know whether I'm the oxy or the moron. But I did find out when I was in politics in Massachusetts that the logical thinking of an engineer actually adds value to the debate of a policy. Engineers are the most ethical subgroup of the American workforce, because engineers have a disproportionate responsibility for making sure what they did was the right thing to do, and they did it in the right way. You don't want people driving over a bridge and having fear that it will collapse, or getting in an elevator and thinking that it will crash, or being in a car and thinking that that airbag won't come out if it has to. Engineers have a conscience, and they live up to the responsibility. So answering the call to be in politics, I think, is really answering a call to be in public service. And I completely encourage you to pay attention to what it means to be in politics and what it means to say yes to the invitation to be part of government. That Declaration of Independence, which happens to be so important to us, really is just an invitation. It's an invitation to be involved in government. Once you get involved, you have an obligation, because you take an oath usually if you win to serve. If you don't win, you take an obligation to pay attention to what your successor may be doing in politics. So I encourage you to have the courage to say, politics is not a dirty word, and I want to be part of the Constitution. And if you're an American citizen, there's no greater invitation than to register to vote, to run for office, to get involved and to make a difference. So I am not the world's greatest engineer. I am an engineer by training, a politician by disease. I'll probably die of it. But I was asked to say, or ask you, how would you like me to tell you how I became Chief of Staff to a President of the United States? First of all, don't apply for it. I don't know anyone who became a Chief of Staff to the President of the United States who applied for the job and then got it. I know lots of people who told me they were planning to apply for it, and I said, you're wasting your time. But so I did not apply to be the President's Chief of Staff, but I think I know why he selected me to be his Chief of Staff. And if you don't mind, can I give you a little talk about how I got to where I was and how blessed I am that I live in this country? I did participate in politics very early, even in high school, but certainly right after I graduated from college. And I supported people who ran for office. I ran for office myself to get elected to the planning board. I ended up running for the state legislature. I lost, and then I ran again and won in a district that was overwhelmingly against me, or not against me, was of a different party. Yes, I am a Republican. I respect Republicans and Democrats and independents. But I was a Republican, and the district that I was running in for legislature was 6-1 Democrat. A Republican hadn't been elected for a long time. And here I was, just newly elected to the planning board in the town of Holbrook, eager to run for the legislature, and I had to run in a district that was 6-1 against me. My own parents said, you're planning to run for the legislature? And I said, yes. They said, my father said, as a Republican? And I said, yes. And he was a Republican, and he said, I think you're not going to win. But I took out the papers, I knocked doors, and I would knock on my opponent's door every time I was out campaigning. I was blessed to say that he was home almost every time I knocked on his door, because that meant he was not out campaigning. But I would knock on my door and I would greet him and say, I just wanted to let you know I'm in the neighborhood, not running against you. I am running for the same seat you're running for, but I have nothing against you. And he would say, oh, you're a nice young kid, have a good time, and he was very comfortable and thought that he would win easily. The campaign, I was really working as an engineer, and I got up very early in the morning and I would take the bus to a spot where I knew people who worked at the Department of Construction or whatever it was. I'd stop into this breakfast place and have breakfast with people and say, I'm having breakfast with you, I'm running for the legislature, I have to go to work after I talk with you. So I would campaign before I went to work in engineering, and then I would come right after work. I would go right out on the campaign trail and knock on doors, leaving work, getting off the bus, knocking on doors, and knocking on my opponent's door. That's at the same time saying, I'm in the neighborhood, it's good to see you at home. Got to know his wife and his kids and everything else. And election day came, and believe it or not, I worked really hard on election day. We had a group of people we called the Dawn Patrol. And I had lots of young people that would be part of the Dawn Patrol and help me get out the vote very early in the morning, and it was a lot of fun to do that. and ended up getting 67% of the vote and defeated my opponent, and he was shocked. But the interesting thing is, 2 years later, when I had to run for re-election, he was one of the first people to endorse me when I ran, and ended up being very close to him, and politics then invited me to do things that I never thought I would do. First of all, there was an election for president. And an election for president starts off with an election for the right to run for president, so you have primaries. I got very involved in campaigning for Ronald Reagan and George H.W. Bush, and there were 16 people running for Republican nomination for president in this election. And I wrote letters to all 16 candidates and heard back from 15 of them. The only candidate in the race that I did not hear from was John Connally from Texas. Everyone else said, thank you for your note. I had offered, in my note, I said, I live in Massachusetts. I'd be glad to meet you at Logan Airport and help you get to New Hampshire, where I know you're going to be campaigning, and I'd like to learn more about you. I heard from everybody except for John Connally, and I got to pick up the candidates at Logan Airport and drive them to New Hampshire and get to know them. I then had strong opinions supporting George H.W. Bush, became his campaign manager in New England, and to make a long story short, he lost in New Hampshire in the primary. He won in Massachusetts for the primary. He then went on to get nominated and became the vice presidential nominee for the Republican Party, and he teamed with Ronald Reagan and ran, and Reagan-Bush actually carried Massachusetts in the general election for the Electoral College, and it was the last time Massachusetts carried their Electoral College votes as Republicans, and so I was very proud to have run that campaign. That gave me an opportunity to then look at other opportunities. I decided to run for governor. I had been the Republican whip in the Massachusetts House. There are not a lot of Republicans to whip in the Massachusetts House. But I got very active in supporting the Republican cause where I believed in it, and I also worked very hard at uncovering corruption in government. And believe it or not, most of that corruption fell some ways close to an engineer's concern. I did have a fellow Democrat who worked closely with me on finding corruption in government and working on it. Actually, there's a professor at the Bush School that also did it, Andrew Natsios. If you ever run into Andrew Natsios at the Bush School, he was part of this effort as well. But I helped. I got a call one day from my friend, a Democrat member of the legislature, who said, I just got a call from someone who said they wanted me to go to a barrel about 5 miles outside of Boston and look for a bag that had some information that they felt should be looked at by someone in the legislature. And my friend said, I'm going to go out and take a look at the bag and see what it says. He said, do you want to go with me? I said, sure, I'll go with you. We got there and found a bag and looked at it and opened it up, and it was engineering plans for the UMass Boston campus. And my friend was not an engineer, he was a lawyer. He said, I have no idea what this looks like. I said, I'll take them and look and see what I can do with them. So I took the plans, and I could lay out the plans on the UMass Boston campus that was under construction. And fortunately, in this packet of information were bills that had been paid. And I could figure out where a bill was paid for concrete, where the concrete would be going at the UMass campus site. So I took the plans out and calculated how much concrete could fit in that wall and compare it to the bills that applied to that wall, and I found that they were paying probably twice as much for concrete as could fit into the wall. I then did the rebars. I said, how many rebars do they need? Calculated how many rebars they needed, take a look at the vouchers that came in, and found that they were paying for more rebars than they could possibly use. And then we took all that information to the executive branch of government, the governor's office. There was little interest in it. I took it to the Speaker of the House, and there was little interest in it. Phil Johnston, the Democrat member, and I said, this is not appropriate. We're going to call for an investigation. Make a long story short, the investigation took over a year. 2 state legislators from the House and 2 from the Senate ended up going to prison, and millions of dollars was saved for the taxpayers. That was very motivating for me to take a look at other challenges. One was, as an engineer, I had been down mapping the cracks in the wall of the Boston Metropolitan Transit Authority, the subway system. And I was an engineer working for a company that was mapping the cracks in the walls, and so I had the privilege of working in the subway system for probably a month or so, mapping their walls and where work needed to be done, and then recommending what their solutions were to help fill the cracks and fix the problems. When I got a call from someone who said, he used the name Lone Ranger, this is the Lone Ranger, and I said, do I know you? He said, no, but I know you. And I have a package for you that I would like to leave at this Subway shop in Boston. Just go and say the Lone Ranger sent you, and they'll give you a packet of information. I went to the Subway shop, walked in the door, and I said, the Lone Ranger sent me. And the fellow behind the booth said, oh, we were expecting you. I don't know what's in this bag, but he really wants me to give it to you. And he handed me a bag, and it was a whole bunch of information about subway cars that were stored in a tunnel in the metropolitan system that were brand new cars, but they were being cannibalized and the parts were being sold. So I said, I know that subway system. And this happened to be in January of the year. It was very cold. I said to a fellow who was a close friend, I said, let's take a run through the subway system today. And we went to the subway system, put on our coats. We sat on the side waiting for the subway cars to come by. They came by. We did not get on, but as soon as they would go, we jumped down into where we're not supposed to jump down, stay off that electric rail, the third rail. And I worked my way to where I thought the subway cars would be, in an abandoned area of the subway. Found that area, found the cars, was able to take pictures of the numbers on the engines and the train cars, and map it all out, find my way to a cul-de-sac which had a ladder going up to a place where I could get out, and freezing cold, we climb up the ladder, push open the steel cover to the ladder, get out. We're in the middle of the Massachusetts Turnpike. Cars are whisking by us, and I have pictures and notes from all these subway cars. And we're laughing hilariously. We're freezing cold, and we're dodging cars trying to get to another street. Make another long story short, we took that information to the MBTA. They denied that they had the cars there. I proved that they did with photographs, and that particular thing caused people to go to jail and learn the difference of truth and justice and doing things right. So I came in with a reputation of using my engineering skills to try to clean up government. But how did I become a chief of staff? Very quickly, I ran for governor, lost in a primary, did better than expected, was called a hidden winner. It's much better to be called a real winner than a hidden winner. I received a phone call soon after the election from a fellow by the name of James A. Baker III. There's a pavilion on this campus now named after James A. Baker III. And he was chief of staff to Ronald Reagan, President of the United States. And he said, Andy, would you like to come work for President Reagan? And I said, I'd love to, I think. Let's see what happens. That was in September of 1983 and 1982. And I then came down to Washington, D.C., was interviewed. In 1983, I started working as a special assistant to the President for Intergovernmental Affairs as the liaison to the nation's governors for President Ronald Reagan. Brought me to Washington, D.C. George H.W. Bush was the sitting vice president of the United States. I had already run his campaigns in New England, and he became even closer friends with me. I worked there. It was a remarkable experience. And then George H.W. Bush runs for president after being vice president. He becomes president. I was part of the campaign, and he invited me to come and work as Deputy White House Chief of Staff. And at least you think I'm the only engineer in government. You should know that I was then Deputy White House Chief of Staff to a very, very prominent engineer, super well qualified, truly the most intelligent person I have ever met, John H. Sununu from New Hampshire, who is MIT graduate, engineering professor at Tufts University. And this is the truth, not hyperbole. His IQ was higher than Stephen Hawking's. He was the toughest person I ever worked for. He did not suffer fools kindly, and I happened to be the closest fool to him every day. But I ended up being Deputy White House Chief of Staff, and then John Sununu left as White House Chief of Staff, and Sam Skinner, who was the Secretary of Transportation, became the Chief of Staff to the President of the United States, and President George H.W. Bush asked me to be the Secretary of Transportation. That's how I became the Secretary of Transportation. So that's experience with George H.W. Bush. George W. Bush, the sitting governor of Texas at the time, was running for president of the United States. I volunteered to help him, and I said, if you want me to help you by being an opponent of yours, I'll do that. If you want me to support an opponent of yours, I'll do that too. But I'll do whatever you think is best. And he knew I was very close to his dad. He was a little skeptical. He didn't want to be that close to his dad. And I said, you can't be any closer to your dad than being your son. So he ended up asking me to help on the campaign. I did help on the campaign. The week before the election, as hanging chads would be showing up in Florida, I got a call from him saying that he wanted to meet me in Florida to campaign the last week of the campaign before the elections. And he said, go to Austin, do not go to the campaign headquarters. I have something I want you to do. Clay Johnson, my chief of staff, will pick you up and make sure you have good information. Do not go to the campaign headquarters. Go to the Stephen F. Austin Hotel. Stay there. I'll call you at 10 o'clock at night. I've got something I want to talk to you about. I went to Austin, did not go anywhere other than the Stephen F. Austin Hotel, met with Clay Johnson. He gave me a lot of material. It was material that related to transitions. I had been the transition for George H.W. Bush out of office. In fact, that's what brought me to Texas A&M the first times, was negotiating the Bush School being there and the Bush Foundation, the library. And George W. Bush asked me if I had the information that Clay Johnson gave, and I said, I have it. He said, great. I want you to come see me in Florida, but I want you first to go see my parents in Houston. So go see my parents, and then tomorrow fly to Tampa, St. Pete, and I'll meet you in Florida. I went to Houston from Austin, drove to Houston, arrived at the president's home. The Secret Service were there. They found out that I was coming, opened the doors for me, welcomed me in. I felt like I was in a museum and couldn't touch anything, and the cameras were watching me the whole time. Didn't know what to do. Finally, President Bush and Barbara Bush come in after campaigning all day for their son, and it was well after midnight. And they said, are you hungry? And I said, oh, I'm fine. Well, we're hungry. We're going to make sandwiches. And we had peanut butter and carrot sandwiches. And they talked about being out campaigning for their son, and they went to bed and said, good night. I went to bed in the guest room. I got up very early the next morning, showered, shaved, made my bed, was sitting in a rocking chair when there's a knock on the door, and it's Barbara Bush saying, good morning, you're already up. Did you even sleep in this bed? I said, yes, I had a good night's sleep. I always make my own bed. Oh, well, have you had any coffee yet? And I said, no. And she said, go downstairs, get some coffee, and then join us. And so I went downstairs to get some coffee, got some coffee, showed up. They're in their bed, in their bedroom. I knock on the door. They open the door. President Bush opens the door. I'm standing at the threshold. He gets back into the bed with his wife, and they're talking about the TV being on and complaining the way their son is being treated. And they're saying things to me like, you know what he's like, and you know what the job is like, so if you can help him. I'm looking forward to you helping him. And going back and forth, and it was a really interesting argument because the president would be commenting on something on the TV, then Barbara Bush would comment on something on the TV or something the president said, and I'm being left out of the conversation, and then they say, come on in, come on in, come on in. And President Bush says to his wife, move over, let Andy get in there. I lay down next to Barbara Bush with my cup of coffee, and they're talking to me with great affection and care for their son. And then the president says, I'm going to go take my shower. So he gets up out of the bed. I get up out of the bed. He goes into the shower room, and he turns around and he says to me, you stay there with Barr. Very uncomfortable, but I have to admit, that's the first time I thought maybe the president was not looking for me to do the transition into government. Maybe it was something else. I ended up flying to Tampa, Florida, and there was a note on my door that I was supposed to have dinner the night before with the president, or the governor at the time, but there was a note saying I was late, so it looks like you should have breakfast. He'll see you at breakfast time, have breakfast with him. So I went to have breakfast with him. He said, how did the meeting with my parents go? And he could tell, or I could tell, that he had already talked to his parents. Then he says, I'm ready to do this. And I said, I know you're ready. And he says, no, I'm ready to do this for you. And I said, what do you mean? He says, would you like to be the big one? And I knew what he meant, chief of staff. And I said, you can't say that to me. I don't want to have a conversation like that until I know whether or not you're the president of the United States. And he said, yeah, you're probably right, you're probably right. I said, well, we'll talk after you win the election. And he said, okay, I want you to go to Austin. I'll see you election night. And I said, I'd like my wife to come with me. And he said, yeah, you should have her down here too. Election night came, hanging chads resulted in no result right away. And the president sends me a note late that night saying, he thinks he's going to do all right. I should come see him in the morning and have breakfast with him at the governor's mansion. Bottom line is that I wake up the next morning, state trooper, I want to say it was actually, says, we'll take you over to the mansion. They take me to the mansion. I go meet with George W. Bush, and he says, I'm going to win this election. I would like you to be my chief of staff. And I said, you and I have to have a candid conversation. If I'm your chief of staff, you have to understand that I cannot be your friend. If I'm your chief of staff, you can be my friend, and I don't want to let you down. But you can't feel bad about being angry with me or firing me or eliminating me because you don't want to hurt your friend. I cannot be your friend. And you have to understand that if I am your chief of staff, I will say things to you that you would not like. And you've got to at least listen to me. He said, of course, I'd have no problem doing that. I said, this is really serious. If it doesn't work out, you have to acknowledge that and tell me it's not going to work out. And I will say, I want you to succeed and get out of your way. And then he said, so you'll do it? And I said, no. I got one other request. I said, my wife is my partner in everything I've done. I would like my wife to have access to the West Wing of the White House because I know that I basically will be spending more time with you than I will my wife if I'm your chief of staff. And he said, Kathleen I said, I just want to make sure she gets a credential and she can come see me in the West Wing of the White House. And I always say, Mr. President, I love you, I want to help you, but I'll never go to bed with you. And I'd like to be able to go to bed with my wife sometime. So he said, yes, of course I'll make sure she has a pass. I said, you don't count. What does Laura think? Because if Laura doesn't want her around, it wouldn't work. And he said, let's go ask her. So we go out to the kitchen, and he says, Andy says he'll do this thing if Kathleen can have access to the White House to come in and see him every once in a while. And Laura said, of course she would. That was how I became chief of staff. The job of the chief of staff is to tell truth to power. The job of the chief of staff is to make sure that consequences are anticipated before they show up, and to make sure that when decisions are made, there are as few unintended consequences as possible. and that people who serve the president don't waste his time. Time is the greatest enemy to any president. They only serve for 4 years, and they have a lot to do. I would tell people who were appointed to work at the White House by the president, I said, the president has appointed you to this position. You've got a title called Assistant to the President, Deputy Assistant to the President, or Special Assistant to the President. You're appointed by the president. You cannot see the president anytime you want to. You can see the president anytime you need to. But I guarantee many of you will pretend you need to when you really just have a giant want. And I said, I will be scratching at your little veneer if I see you in the Oval Office. And if I see a thin veneer of need covering a giant want, you won't have access to see the president anytime you want to. So that was the way that we functioned. President Bush and I are both the same age, so we had a great, candid relationship. Ronald Reagan was candidly like my grandfather when I worked with him. George H.W. Bush was like my dad when I worked with him. And you know, if you argue with your grandfather, you apologize pretty quickly. If you argue with your dad, you think about it and then apologize 3 or 4 times to get over it. George Bush was like my brother. I could say, "What were you doing, you idiot?" And he would say, "What are you doing?" And we'd go right at it. But that's the difference. So that's how you became Chief of Staff. And no, you don't go to monster.com to get an appointment. And Indeed is not the right website to go to and say apply for the job. With that, I say, you are engineers. You are in the best school of engineering in the world. I think, well, MIT's got a pretty good record too. But you should take advantage of this phenomenal institution and take advantage of the Bush School as part of your thinking. Why? Because engineers actually solutions to governmental problems. Many of the challenges in the executive branch of government relate somehow to either transportation or structure or discipline or safety. And it's very important that engineers recognize what is going on in the country, and that means to pay attention. There are only 10 members of the United States Congress right now who are engineers. 9 of them are in the House, 1 of them is in the Senate. There is room for you to be a member of Congress or a senator, and we'd love to have you think about taking a path in public service. The intelligence community needs engineers. The Department of Transportation needs engineers. The Department of Housing and Urban Development needs engineers. Naval reactor programs need engineers. The truth is our Defense Department needs engineers. There are plenty of opportunities. If you're an engineer and a politician, you are not an oxymoron. You're actually a noble public servant if you say yes to that. So I'm going to plead with you to get out there, find out what it means to be a registered voter, register to vote, maybe think of running for office, or maybe think going into the noble public service that the Bush School of Government and Public Service invites you to do, and work with people that make a difference by serving in government. And you've got a lot of good local officers that you should be understanding in what they do. And you're in the midst right now of a tremendous boom in what it means to be an engineer because of artificial intelligence. I hope none of you fall into the trap of believing you are artificially intelligent. You are not artificially intelligent, you're intelligent. And I plead with you to have an open mind, an open heart, and a conscience to make sure that your intelligence is part of the solution and people have a chance to respond to it. So with that, I say thank you very much. I'm truly honored to be recognized as an engineer. This award will have me be very embarrassed because I know it looks better than I am. But I'm very grateful for the opportunity to be here, and I actually celebrate you, and I hope that you will have the courage to say you can make a difference in politics. It's not a dirty word. thank you, God bless you, and giggle.
So 43 years ago, my grandfather passed away, and within about 10 years, his colleagues and students, folks that he had known, put together an endowment for the Buchanan Chair. And here we are 33 years into Dr. Briaud's amazing sponsorship and management of the Buchanan Chair. I'm always privileged and humbled when he gives me an opportunity to be involved in this day. I want to thank you for your service to our country, and a special thanks for coming and helping us perpetuate this legacy. Let's
This was truly unexpected, and I'm not worthy, but I'm grateful. And I'm really honored to be here, and I thank you and the legacy that you've inspired. I thank you and the leadership that allows this legacy to always be remembered. And I thank all of you for having a chance to participate and meet remarkable people and Forrest Gump.